Once again, so we are going to stick with this kind of geometric construction. And here you have question, right? So if we consider a point that has been labeled as one by the perceptron, right? So it is part of the positive class, right? In which case, what that means is that this point lies above the decision boundary line or plane, or whatever, right? So the question is, what is the angle made by this point vector with the weight vector, right? And the way you think about it, basically, is that so I will say, because that is how I have discussed the solution. Yeah, so because that is how I have discussed the solution, you can consider a two-dimensional case, right? Uh, and try to work it out from there because it will be simpler, easier to understand in a two-dimensional case, right? So yeah, once again, I will give some time to people to work it out on their own, and then we will look at the solution. Specifically, I will kind of explain uh, explain the geometry of how it happens, why this happens, right? Why it is how it is. Okay, so um, yeah, so see, some people have answered. Uh, Less than or equal to yes. So basically correct. The angle will be less than or equal to 90 degrees, right? And we'll see why that is, right? So like I said, for simplicity, you can consider two input. perceptron, but the, the the consideration, it does not change. The answer does not really change depending on how many inputs we are considering. Okay. So basically, for a two-input perceptron, you write the equation like this: W1 plus W1 x1 plus W2 x2 minus theta equals to 0. And the point will be labeled 1 if W1 x1 plus W2 x2 minus theta is greater than 0. So this is what I had previously, but you can change this greater than to greater than equal to if that is how it is being currently taught in the course, right? So yeah, so like I said, so you change this equation. The only difference is that if something lies on the plane, it will be considered as part of the positive class, right? So here we have a construction of what this kind of what such a you know what this question description would actually look like, right? So you have x1, x2, which are your two axes. You have a decision boundary line, right? Which is shown in red, and you have a positive sample which is shown in blue, right? And the point vector looks like this, and the weight vector, obviously, like I said, the weight vector is the normal to this decision boundary line, right? So the weight vector looks like this, and obviously you can see that if a point lies in this region, right? If a point lies basically above the line, uh, angle made by that point vector and the weight vector will always be less than 90 degrees, right? If it lies on the decision boundary line, then the angle will be exactly 90 degrees. If it lies below the decision boundary line, that angle will be greater than 90 degrees, right? So, it will be an obtuse angle that will be formed if it is a negative sample, right? So, if it is a positive sample, or rather, if it is being currently classified as a positive sample, then the angle made by the uh, point vector and the weight vector will always be less than or equal to 90 degrees, depending, it will be that. Here I have mentioned less than 90 degrees because I was considering the convention that, you know, this this value has to be greater than 0 for uh, classification as a positive sample. If you are considering greater than or equal to, then angle will be less than or equal to 90, right? So yeah, so basically this is what this is, and this is kind of uh, crucial also so this geometric conception of this like I said, these angles and this inner product formulation kind of becomes crucial to how you actually optimize these perceptrons, right? So here we come to something else, something interesting, right? So you have previously we considered some Boolean functions for McCulloch Pitts, right? We considered like four input AND functions with negations and stuff like that. We considered OR functions, right? And in all of those cases, we were able to make a McCulloch Pitt neuron that represented the truth table of that Boolean function, right? But that is not always the case, right? And uh, so the interesting question arises is that when is it not the case, right? And of course, know, because we saw uh, once again, if you bring the geometry angle into it, basically you will realize that what McCulloch neurons were doing in a very limited sense was it was drawing these linear boundaries, right? And linear boundaries, obviously, I'm saying that they are generically defined as linear boundaries, right? Of course, the exact form of that boundary will change depending on how many inputs we are considering, right? So for a two-input case, it will be a line. For three input, it will be a plane, and so on and so forth, right? But they are all uh, still linear division boundaries, right? And the problem with these linear boundaries, of course, is that they can only divide uh, classes when they are linearly separated. And one of these example of the excuse me, one of the example uh, functions that is actually not linearly separable is the sort function, right? So you have a uh, even like two input sort function. Uh, this is not linearly separable, and we can figure it out very simply just by drawing the points, right? And you mark them as either like one uh, positive samples or negative samples, right? Positive samples meaning the ones that will give you an output of one, negative samples are whatever will give you an output of zero, right? And if you draw the Z function, basically on two inputs, right? You have 4 points, right? 0, 0, 1, 0, 0, 1, and 1, 1, right? Your XOR will give zero output at 0, 0, and it will give a zero output at uh, 1, 1, right? And it will give one output at uh, 1, 0, and 0, 1, right? Obviously, right? This is the very simple definition of the exclusive OR function, right? And here you come across the problem that there is no way you can draw a line, right, which divides this which divide this space in such a way that all of the red points lie on one side and all of the blue points lie on the other side, right? So let's think about it for a second. You know, it's obviously impossible to draw a line that divides this two classes cleanly, right? And so that is why we say that this is not linearly separable, right? And because it is not linearly separable, it can never be represented by McCulloch Pitts neurons. In fact, it can uh, never be represented by a single perceptron also, right? So, I mean, and of course, I'm saying, it cannot be represented by one McCulloch Pitts neuron, and it cannot be represented by one perceptron, right? But yeah, so this is the kind of obvious. Uh, that is why I was kind of specifying the fact that they cannot be represented by one neuron, because obviously you can represent them with multiple of these neurons, right? So if you build the truth table step by step, right, you will basically have a situation where at like the smaller parts of the truth table will be represented by linearly separable uh, linearly separable functions, right? And then you can fill those linearly separable functions and uh, with multiple numbers of McCulloch neurons you can basically build out this function, right? And as someone uh, mentioned in the chat, it is possible with with three McCulloch neurons, right? And the idea is very simple, right? For XOR, for exclusive OR, you have this OR of two quantities, right? So you have x1 x1 and not x2 is one quantity, and the other quantity is x2 and not x1, and then you take an OR of those two quantities, you'll get the exclusive OR, right? So each of those three things can be individually represented by McCulloch neuron, right? So you can represent x1 and not x2, right? Which is this green neuron over here, x1 and not x2. X2 is going as a inhibitory connection, and theta is set to 1. And this blue neuron here is x2 and not x1, right? So x1 is going as a inhibitory neuron, x2 is going as an excitatory neuron, theta is 1, right? So these two neurons separately compute the two uh, the two parts uh, of the excuse me, of the Zord function, and then what is left is just to take the OR of that, right? So you take both of these, go into a third neuron, which has theta equals to 1, which is the standard setting for an odd function, right? And the output will give you the exclusive one, right? So in this way, if you kind of break down the function into the uh, component into its like different components that can be either combined by AND functions or OR functions, then you'll basically have a situation where, within uh, two layers, you can basically you can represent essentially uh, every possible Boolean function, right? This also comes into when you talk about multi-layer perceptrons. There is this concept of universal function approximators, right? And for example, for Boolean functions, it is like uh, these are kind of mathematical results that you can go into more details, but essentially the idea is that if you have a network with at least one middle layer, right, then you can approximate any function, right? And this is very easy to show uh, for Boolean functions, right? Essentially, in the middle layer, uh, you basically combine like all of the uh, component parts that you can get, right? And then the final layer is like a or uh, or combination of all of the all of the smaller parts of the Boolean function, right? You can always divide a a complex Boolean function in such a way that it becomes a it becomes like a collection of these odd functions, right? And in that way, you do like a universal approximation. Uh, it's not even an approximation; it's like a universal representation uh, thing that you can do with perceptrons. You can even do it with this McCulloch Pitts, right? So yeah, so then we come to something uh, interesting, little bit. This always interests me. It's uh, the idea that coordinate transformation, right? So basically, your perceptrons, right, uh, will always do, like I said, it will do a linear cut, right? A, it implements a linear decision boundary, and a linear decision boundary uh, will always act upon linearly separable data, right? That is that is the main idea. And so here is a situation if you consider deep networks, right? Specifically, I'm talking about uh, classification models, right? Uh, where you try to classify inputs into different number of classes. Could be like two classes or multiple classes, whatever. It does not really matter. Uh, Essentially, the final layer of your network is always going to be uh, some kind of a you know uh, linear uh, classifier, right? Because the final layer will always have like this weight matrix, and then you kind of apply this whatever like softmax or something, right? So it approximates as a uh, linear separator, right? But the the advantage of having deep networks is that typically, even if your data is very mixed up, very jumbled up, right? If it is not linearly separable, even in those cases, you can always figure out, a decision boundary uh, that makes it finally you are able to decide whether something belongs to one class or not, right? And why are we able to do this? Uh, one of the ways that you can look into that you can consider why we are able to do this is the idea of coordinate transformations, right? And basically, let's say you have data that looks like this, right? So this is a two-dimensional data, right? So you have x1 and x2, and you have one class which is represented by uh, blue dots. You have one class which is represented by red dots, right? And obviously, you can see here, just by inspection, you can say that this is not linearly separable, right? But of course, there is a structure to this data, right? This is, you can obviously see this is like concentric circles that that have appeared. And because there is a structure to this data, this is like a simplified case, which is why this is a simplified case so that you can make this assertions or make this reach this conclusion just by inspection, right? Uh, but in general, there will be some pattern. There will also be some pattern or some structure to the data that allows your neural network basically to separate them, right? In this case, it's a very simple pattern that you can notice, and we can obviously take advantage of this if basically if we just take these points from Cartesian coordinates to polar coordinates, for example, right? So if we go from Cartesian to polar coordinates and we draw the points again, right? If we draw these points again, basically you'll have two straight lines that you occur at different radii, but obviously because they are circles, they just go up and down, right? And obviously you can see here in this coordinate transform, these are linearly separable. Then you can just draw a line in between this, and you get two different classes, right? So this is the basic idea of coordinate transformations, and this is one of the ways that you can think of. You can think like you can think of how deep neural networks work. The basic idea is that the the parameters in the deep network, they eventually kind of figure out the structure that exists within the data, right? And then what it does is that it unravels that structure in such a way that the final layer can act as a simple linear classifier and divide everything into the respective classes, right? So that is one way to think about how uh, deep neural networks work, right? Which is this idea of kind of learning the hidden or inherent structures that are present in the data, right? And then unraveling the structures such that finally we'll have a situation where everything is neatly separable by uh, straight line boundaries, right? So yeah, so basically this is kind of it's a little bit out of you know what will be typically covered in the course, but it's just one of it's just like an interpretation of uh, how things happen, right? And one of the things that is important in this, obviously, is the fact that we have non-linearities in the network, right? Which is very, very important. The fact that you have these activation functions in each of these layers, which impose these nonlinear functions on the outputs, right? Is very, very important to do this kind of thing, right? Because if you think about, how do you go from Cartesian to polar coordinates, then it goes to, uh, it's like how do you get the radius? It's the square root of x1 squared plus x2 squared, right? That's how you get this r, and you get theta by, tan inverse of uh, x1 by x2, right? Or x2 by x1, right? So that's how you get this phi, then you get r, right? And you'll notice that both of these functions are obviously non-linear functions, right? They are not, they can be, they are not like described as linear functions which are similar to how you write uh, lines or planes, things like that. Right? And that is why having nonlinear uh, these nonlinear activation functions is very important, right? Because those nonlinear activation functions essentially allow this kind of nonlinear structure to be removed from the data, to be unraveled from the data. Right? So yeah, so that is the end of the content that I have prepared for this session. Uh, anyone, so if you have questions, you can ask, and if you have doubts, even uh, based on things that was covered earlier, you can ask. Uh, yeah, if you are not having doubts or questions, I think you can leave the call. Yes. Notes के लिए I'm not sure. I mean, anyways, you're doing the course, right? Uh, as a reference, you can look into. So there is this deep learning book by Ian Goodfellow. Specifically this in solution to